My brief talk, 15 minutes today, was inspired by a talk last year that was given by Karl-Heinz Meyer. And in that talk, one of the many things you were talking about was the capabilities of the system that you were building. And you had mentioned, incidentally, that one of the benchmarks that you're using to demonstrate the capability was Eugene Itzekevich's collection of benchmark neuron patterns to verify sort of test benchmarks for simulating the behavior of realistic neurons. And I realized at that time, many years ago when I was at Caltech, so 25 years ago when I was at Caltech, as a side project, I built an event-based neuron simulation. And when I saw Eugene's list of neuron patterns last year, I realized, I wonder if this old simulator that I had written would be capable of simulating that modern benchmark. There was no benchmark systems like that to compare to in 1993. So I took a look at that, and so that's what I wanted to show today. When I told Eugene that I had done that, he said, "Oh, that's interesting. You should publish that." And in fact, last night at dinner with Paul and Karl-Heinz, Karl-Heinz said the same thing. "Oh, that's interesting. If this simulator, this event-driven simulator, can do that, you should publish that." So I thought, we all thought that this might be something that would be of interest to the community. So here I want to just give a brief history, as I see it. I haven't seen this published anywhere else, but an early history of event-driven spiking neuron simulation. I think most people would say that began sometime in 1999 or 98. That there was a beginning of real interest in that with NEST, Synod converted into NEST, SpikeNet 98, modern talks, today's talk by Chris Carlson on CarlSim is the modern embodiment of that in its much more mature form, GPU enabled and so on. But you may not realize, as far as I know, the first event-driven simulation of spiking neural networks was done by Gil Pratt in his PhD thesis, Pulse Computation at MIT. Now, Gil Pratt, we know that name. He's a program director at DARPA. So there's a long history that goes back, as far as I know, begins with him. Ralph Etienne Cummings today mentioned in the to spike or not to spike, and mentioned the important role that John Lazaro and Misha Mahawald played. Yeah, they were really important, and in my development as well there. John Lazaro had built an analog simulator, schematic capture that was intended for analog circuits, since that's what we were doing in Carver Mead's lab, but it had an embedded simulator inside it, and that was called Analog. Misha Mahawald was working with Rodney Douglas on her advanced neuron models implemented in VLSI, analog VLSI. I was inspired by both of those, but since I'd been a chip designer in the 1980s, what I was interested in was the equivalent of Mentor's QuickSim, the very fast event-driven digital simulator that you use for simulating an entire chip. You don't use SPICE to simulate an entire chip. You use QuickSim or some tool like that for simulating the large, millions of transistors and circuits on a huge chip. What I thought we needed was something like that. So that's what motivated me to try building an event-driven simulator. So published some papers in 92, 93, and the code is still available on my website. I don't recommend that you use it. You should use CarlSim 3.1, and I asked, I'll tell a bit more of that story later, but 3.0, extremely interesting, but in a minute you'll see why I would recommend 3.1. So anyway, that's the history as I see it of event-driven simulation of spiking neural systems. So what I wanted to show you was the thing that motivated me from Karl-Heinz's talk about Eugene's set of canonical neuron patterns. The question is, can that be simulated by an event-driven simulator that has a point neuron primitive and does not do differential equation solving. I think that there's a general perception in the community that that's too simple a model to do anything that's realistic. That's the point of this talk, is to show you how far you can get with such a simple primitive, provided that you're willing to concatenate and conglomerate some of those primitives into more interesting and useful larger functions. So this is the basic element. The first thing is just a neuron that has a tonic input. So this is the symbol for the neuron that I created in John and Lazaro's analog tool called, I renamed Neurolog. So there's the tonic input to the dendrite. The dendrite is that line there. There's the cell body, and it's a point, and it does exactly what you'd expect. The tonic current causes it to charge up. It fires an instantaneous spike. The refractory period is 0. That's the parameter there. And so it simply spikes forever once the tonic thing turns on. Totally simple. Nothing to that. The next thing is you can build up what you might think of as a composite neuron. I called it a super neuron at the time because I was thinking this is like a single neuron that has the behavior of spiking bursts, or a bursting behavior. I had to build it out of two what I called neural primitives, but I was really thinking of this as a single super neuron that had this behavior. So it starts with the same thing as before, a tonic input that causes this first neuron to fire repeatedly with a very weak excitatory input to the second neuron. And so it takes about 5 or 10 spikes to charge this thing up to the point where it finally fires. And when it does fire, it fires a very strong and quite long-lasting inhibitory input to this one, which turns it off for a certain amount of time. And so that's why it fires for a while and then gets turned off by the second neuron. And then finally the current pulse that came from this inhibitory input turns off, and then the whole process repeats. So we get that bursting behavior. You see this C tonic bursting. C, that's because that's Eugene Izhikevich's third of his many patterns. You probably recognize that, and I'll show you the whole picture in a minute. But the first one was A, tonic spiking. That's his first pattern. C is the third one. Now, this is where it gets interesting. And this is where I have the impression that the perception that you can't do enough with event-driven simulation may come from. In order to get something like an adapting behavior, like a calcium adaptation, you do have to do something different. This is what I sort of felt was the necessary ingredient to allow you to get something like a calcium buildup that results in an adapting firing rate. Okay? So here's how that works. Here, in addition to the circuit elements we saw before, tonic input causing the first neuron to fire, every time the neuron fires, now it has an inhibitory self-feedback loop. Every spike causes it now to put another current pulse, an inhibitory current pulse, onto itself. That's like the inhibitory effect of calcium buildup in its channel. And there's an important, it's the tiniest of innovations here, but you notice that there's a third parameter on that neuron. There's the strength of the current, there's how long is the current pulse, a rectangular pulse, and there's a third parameter which is what is the accumulation that is permitted. So up to 8 pulses are allowed to accumulate in a summing way. That allows you to embody the accumulation of some state, and that becomes a primitive that can be used. So now you can see for each time there's a pulse, or each time there's a spike at the output of neuron 1, then you get a new current pulse. And then the next time it takes a little longer because there's a bit more inhibition, and this state slowly builds up until finally the broad inhibition occurs that defines the bursting, and then finally the whole thing, the tail end of all those pulses run their way out. So with nothing but rectangular pulses, the circuit by itself creates something that looks suspiciously like an exponential rise and an exponential decrease. There's no exponentials being computed anywhere in the simulation. It's all predicting a time event for a linear current pulse. But the behavior of that accumulating synapse is what makes that possible. To me, that's what made this thing potentially powerful, and I wanted to let the community know that that capability is what makes it happen. Actually, I'm going to want to talk to Chris about whether or not Carl Sim includes that. It must include some feature like that. I assume it does. So I would assume that a modern 2015 vintage event-driven simulator would do this and much, much more. But this was possible a long time ago. Okay, so that makes it possible. That's the magic happens with that summating synapse. This was the first use of the simulator for a biological circuit. So in Carver's lab, Sylvie Reikebusch was one of the students that was working on central pattern generators in Locust as co-supervised by Gilles Laurent at Caltech. And they were, of course, interested in biological realism. She was struggling at that time. In '93, Neuron and Genesis were the differential equation simulators that they can use. And she basically had been working for a whole summer trying to get this 10 neuron circuit to simulate. And it was taking weeks to do the simulations, and she couldn't converge the design because the design cycle was too long. So I said, well, maybe this new simulator can help. In an evening, we got it working, matching her data, and it ran in 3 seconds. It's 1,000 times faster to do event-driven simulation than it is to do differential equation solving. That's why we do design chips that way. So anyway, she was thrilled to get that result. I think that played a role in her thesis work. But it was the first time we had a biological circuit actually modeled with this approach, as far as I know. Finally now, this is what I call, I don't know if it's the right word for it, but it's a Cabbage Complete, right? If it's a benchmark system, can you see the series of patterns? I hope this is a familiar layout for those of you that know Izhikevicius's work, but basically every one of these pictures that look visually identical to Eugene's published paper, all of these were created using the event-driven simulator. And my understanding is that Carlson can also do this, but in version 3.1. 3.0, not yet, but in 3.1, which is coming very soon, it can. So just, I'm not going to go through all of them, but just to give an example, this is the code that describes the circuit that does the first one, which we actually looked at before. It's a neuron with it's actually just a neuron with a tonic input, but because his pattern showed a starting pulse to begin the tonic, then it's got an input that begins it, a synapse that gives that tonic current, and that's the neuron. So that's it. That's the code that makes that pattern happen. The tonic bursting one is this code. It has the 2 neurons, the self-feedback loops. So we've already looked at that, and it looks like that. Now, I will admit that at the bottom of these patterns here, they're really complicated. Now, I don't know how hard Eugene had to work to get those patterns out of his 5-parameter differential equation thing, but I would be willing to bet he had to work pretty hard to find the parameters that made exactly those patterns, and I will confess I had to work pretty hard too to get my thing to match his patterns. But the point is, it can be done. If you're willing to put enough little circuit elements, compose them together, you can make patterns that visually match exactly the patterns that he showed. So it can be done. That's spike. So spike pattern P is the one, the self, what's it called, bistability. A pulse comes in, the same pulse that comes in and turns the thing on can also come in and turn it off. Okay, well, it took 20 minutes to figure out how to do that, but it can be done. Okay, the last comment is about dendritic trees. Now that's a very interesting thing, and I talked with my friend Paul Rhodes, who is a real dedicated on the subject of dendritic trees and neuron and axonal growth, doing learning and plasticity in a very biological, realistic way. Now, for this, I don't have a worked example. That's something I would like to do. But what I wanted to say was that my belief is that even though the simulation primitives are just a point neuron and a summating synapse, that you could simulate the behavior of the nonlinear aggregations in a dendritic tree by using it's basically a compartment model where each compartment is composed of a little neuron and a little set of summating synapses. That you could in some way build up a set of primitives that would allow you to get the benefits of the 1,000-fold increase in speed of event-driven simulation, but you have to compose it in a way that may take a little bit of effort. But I believe that should be possible. Finally, a couple of other examples. Oh, gosh, that's really hard to see. But it's basically effectively a little neural linear feedback shift register, a shift register that has a little inhibitory side channel that feeds back in, so you can get a chaotic spiking behavior out of that. It just happened to be a simple example that I thought was interesting. So in conclusion then, event-driven simulation is capable of realistic spiking neural behaviors, even with its very simple point neuron integrated and fire primitives. But in order to compose that into something that really would be useful to a practicing person in the field, you have to combine those primitives to get realistic behavior. As far as I can tell, it requires the summating synapse to get those calcium-like adaptation behaviors. But if you're willing to do that, the benefit is fantastic. It's 1,000. So my studies said it's 1,000 times faster. And as far as I can see, what Chris said, no, it's 65,000 times faster, because you were saying with the GPUs, it's 65 times faster than it is on the CPUs. So 65,000 times faster for your simulations if you're willing to set it up with the slightly reduced accuracy and the level of abstraction. One other thing that prompted me to think about the talk today was last night. It actually began when we were talking about the problems of doing the differential equation solving. Because differential equation solving is so expensive computationally, you're tempted to take long time steps. And the favorite time step apparently is either half a millisecond or 1 millisecond. Okay? The trouble with doing that, so you bring your computation down reasonably by having long time steps. But the trouble is now you may enforce an accidental synchrony. So now spikes can only happen on your 1 millisecond grid. And spikes that if you had a really fine time grid would have happened 30 microseconds apart are now going to in fact be artificially synchronized by this timing grid. Well, that doesn't happen with event-driven simulations. That's a float. Time is a float in your registers, and you know exactly that there's a time difference. If you're modeling something like intraoral time difference in the auditory system, you can get your 6 microsecond time difference and not be forced onto the grid. So last night I realized, no, event-driven simulation isn't just sort of the weaker younger brother of the manly way to do it. No, actually, in that element, it's actually better than a compromised differential equation solver with too long of a time step. So in fact, event-driven simulation may be better than differential equation solver in some ways. Finally, it may be useful not only just for fast simulations of large networks, but the fact is, if you can run this code in simulation, now if you have something like Steve Ferber's beautiful Spinnaker system or Karl Heinz's beautiful, well, actually I guess it would make most sense on Steve's system because he has all these ARM cores. So you could run an event-driven simulator in every one of those ARM cores as an alternate way of implementing your network. Now, it may or may not be preferable, but this doesn't have to be just for fast simulations. It could actually be the code you run on your dedicated neural hardware if you chose to implement it that way. Okay, and if you do happen to be interested, it's on my website. Historical interest, I guess. Okay? Yeah.
Okay. So maybe Rob can come set up, but I have a quick question for you. So I once went to Eugene Zakevich, and we sat down and tried to fit some neurons using his method. And like you said, it takes a while.
Yeah, you have to work at it a bit.
And it seems like what you talked about is kind of a phenomenological model, right? The advantage of, say, Hodgkin-Huxley or differential equation model is there is some physics underlying the system that lead to those equations.
Yep.
This is phenomenological, so it requires this sort of
Black
human
art.
intervention. Yeah, black art.
It totally does. It does do that.
So do you see a way that you could go from, I sketch out a little trace on a, notepad or whatever, and you fit it, kind of in the way that Chris talked about with STDP?
Well, I mean, that's kind of what I had to do with Sylvie. She was the neuroscientist who had a real circuit, and I had to fit it, find the level of abstraction that made sense. She didn't need adaptation, for example. She just needed lots of spiking things. But I'm not aware of an automatic way of doing it. Any more, for example, you can say the same thing. Transistor simulation with SPICE is pure physics with all the equations, but QuickSim doesn't do any of that, and you live with some degree of abstraction.
All right, thank you, Lloyd.
Yep, thank you.